Hey guys, welcome back to another video. In this session we'll be looking at yet another application of Newtonian mechanics, namely the force of drag. We'll be solving two real-life problems where the force of drag makes a significant difference in the motion of an object. And as always, I will be solving these exercises step by step to avoid any confusion along the way. And if you enjoy these videos, consider giving them a thumbs up, which helps out tremendously. In a nutshell, the force of drag prevents objects from accelerating forever. It's basically a frictional force between the surface of the object and the medium in which it is traveling, and therefore it always points in the direction opposite of the object's motion. Microscopically, it results from the numerous tiny collisions between the object and the molecules of the medium around it, for example the air molecules. The magnitude of the force of drag is equal to 1/2 times c times a times rho times v squared. Now, what do all these quantities mean? C is an aerodynamic constant, which basically says something about the shape of the object that we're looking at. Shapes that are more aerodynamic will have a much smaller constant. A is the cross-sectional surface of our object. For a sphere, it will be this surface, and it basically says that larger objects will experience a larger force of drag. Rho is the density of the medium through which our object travels, and this encapsulates that it is much harder to run in water than it is in plain air. And finally, v is of course the velocity of our object, and we see that the force of drag dramatically increases with the square of our velocity. This shows that the faster we go, the force of drag will quadratically increase, and thereby making it more and more difficult to accelerate to an even higher velocity. In the first exercise, we are going to be looking at why heavier objects seem to be falling at a faster rate than do lighter objects, even though we've always been told that all objects fall at the same rate, whatever their mass. Now, this is of course still true. However, it is only valid when we don't take into account the force of drag, which is what we will do in this exercise. And to make this comparison, we will look at the terminal velocity of a lead ball versus a ball made out of styrofoam. But before we get into that comparison, let's first of course talk about what terminal velocity actually is. Let's say that we have an object which is in free fall, so it's falling towards the earth. Let's also, for good measure, define our x and y coordinate system. So we have our x coordinate system in this way and our y coordinate system perpendicular to that. So we see that our object will be falling under the force of gravity towards the ground in the negative y direction. So this will be the force of gravity. Now, as we have seen, the magnitude of the force of drag is equal to 1/2 times rho times c times a times v squared. And what is most interesting here is this v squared. So we see that as our object increases its velocity while it is accelerating towards the ground, the drag force will be increasing. This means that when our object is still falling at a very slow velocity, because it's only falling for some moments, the force of drag will be very small, because this v is very small. However, when the velocity increases, when time goes on and our object keeps accelerating, the force of drag will keep on increasing as well. And at some point, the force of drag will actually be exactly equal to the force of gravity pointing downwards. And in this case, both forces, or the magnitudes of these forces, they cancel each other out, which means that there is no net force and therefore no acceleration. And at this point, we have terminal velocity, which means that it is the velocity when the acceleration vector is equal to 0, and hence the name terminal velocity. It is the final velocity and the object will not be accelerating any further. And we know that the acceleration is 0 when the net forces acting on the object are of course 0, which is of course a direct consequence of our trusty Newton's second law. F is equal to m times a. And because we know that the net forces have to be 0, so all of the forces have to cancel each other out, we see that at this point, at this terminal velocity, the magnitude of the drag force has to be equal to the magnitude of the gravitational force, because at this point they cancel each other out perfectly. Now, filling in expressions for both of these forces, because we know the expression for the drag force right here, and we know, of course, the expression for the gravitational force, which is simply the mass times the gravitational constant. And so this has to be equal to the magnitude of the drag force 1/2 times c times the density times the surface times v squared, its velocity squared. And at this point, this velocity is not just any velocity, it is the terminal velocity, because when these two forces are equal, that means that our velocity will be the terminal velocity and our object will not be accelerating any further. Therefore, we can rewrite this equality sign as a function of this terminal velocity. And we get that the terminal velocity squared is equal to 2 times the mass times the gravitational constant divided by this constant c multiplied by the density multiplied by the surface. And we can ultimately get this square to the other side, which then becomes a square root. And we have a very nice expression for the terminal velocity of our object. And with respect to the exercise that we're looking at here, whether a lead ball will fall faster than a styrofoam ball, we see that we have the mass here in the enumerator, which means that the terminal velocity will increase if our mass increases. And from this alone, we already see that a higher mass, meaning heavier objects, will have a larger terminal velocity. So given enough time to accelerate, they will actually have a much larger velocity and therefore fall much faster. With this formula at hand, let's now tackle the problem of the comparison between these two balls. And of course, to make a fair comparison, both balls have to be identical in shape. And therefore, let's say that both balls have a radius of 5 centimeters. Of course, since lead has a much higher density, even though these balls have the same volume, the lead ball will be much heavier. So let's see which quantities we need in order to calculate this terminal velocity. The first one is of course the cross-sectional surface. And for a sphere, this will simply be a disk with the radius equal to the radius of our sphere. So the surface of a disk is simply pi times the radius squared. Now we know that the radius in this case is 5 centimeters. So the surface will be pi multiplied by 5 times 10 to the power of minus 2 meters squared. And I already write the centimeters in terms of meters, being 1 centimeter is 0.01 meter or 10 to the power of minus 2 meters, in order for, in our final formula, easily check the units. So we already have one of the quantities that we need. The next quantity is the density of the medium that our object is traveling through. In this case, it is simply air, so we need the density of air. This can be simply looked up to be 1.2 kilograms per cubic meter. The next quantity is this aerodynamic constant, which for a perfect sphere is approximately equal to 0.5. And in the next exercise, we will look at a nice example that illustrates this aerodynamic constant. So what else do we need? Well, we have our surface, we have our density and our aerodynamic constant, and we see that we need two more quantities, namely the mass and the gravitational constant. The gravitational constant we know already to be 9.81 meters per second squared. And now we need the mass of our object, which in this case will be two masses, the two masses of the balls that we are comparing. For the lead ball, the mass will be approximately 6 kilograms, whereas for the styrofoam ball, the mass will be around 50 grams or 0.050 kilograms. And this is indeed a very large difference, but just imagine how different styrofoam and lead are. So these are the two masses that we will be comparing. And at this point, we have all of the quantities that we need to calculate the terminal velocity. So let's first look at the case of our lead ball. We know that the terminal velocity is equal to the square root of 2 times the mass, so 6 kilograms, multiplied by the gravitational constant, which is 9.81 meters per second squared. And now we have to divide this by c, so this will be 0.5, multiplied by the density of air, 1.2 kilogram per cubic meter, and we have to multiply this by the cross-sectional area, which is of course pi multiplied by this 5 times 10 to the power of minus 2 meter squared. And we extend the square root. And at this point, it is always a good idea to check our units. We see that we have velocity that we need to end up with, so we need to have units of meter per second. So let's see which units cancel and which ones don't. We see that this kilogram here and here cancel each other out. And also in the denominator, we have this meter squared, which cancels out with this meter cubed, which is in the denominator of the denominator. And what we're left with is simply 1 meter in the denominator of the denominator, so this will become 1 meter in the numerator. And we see that in the numerator, we already have a meter per second squared. So if we multiply this meter with this meter per second squared, we get, of course, meter squared per second squared. And of course, taking the square root of meter squared over second squared ends up being meter over second. So our units exactly check out. So now that we have the units right, let's simply plug these numbers in a calculator to eventually find the result of 160 meters per second. And this will be the terminal velocity of the lead ball, which is quite fast indeed. So let's now compare this with the styrofoam ball. In this case, the only difference is that our mass, which was 6 kilograms before, is now 0.05 kilograms. So we can basically recycle a lot of what we had before. So we have the square root of 2 multiplied by 0.050 kilograms now, the mass of the styrofoam ball, multiplied by 9.81 meters per second squared, and divide this whole thing by the same denominator, 0.5, multiplied by 1.2 kilogram per cubic meter, the density of air, multiplied by the cross-sectional area, which is of course equal between two balls, because otherwise this would be a quite lousy experiment. So this becomes pi multiplied by 5 times 10 to the power of minus 2 meters, which is 5 centimeters, and we square this to get the area of the cross-section. And we complete the square root. The units, of course, will be again the same. We are not going to check that again, which will be meters per second. And so if we calculate this terminal velocity, we will get approximately 14.77 meters per second. And this is more than 10 times slower than the terminal velocity of the lead ball. So if we drop these two balls from a tower, given enough time, the lead ball will travel at a velocity that is more than 10 times faster than the styrofoam ball. And this difference is only due to the presence of the force of drag. If drag was not present, so for example in a vacuum, then both balls will fall at the same rate. Let's now go to the second and final exercise, which is a short one. In this exercise, we look at the significance of this quantity c, the aerodynamic coefficient, which basically tells us something about the shape of the object that we're looking at. And also in this exercise, we compare two scenarios. However, this time, only the coefficient c will be different between the two. And for both of them, we will calculate the terminal velocity and compare this result. In the first scenario, we have a person that is going towards the ground through the air with a parachute deployed. And because of the drag force, this person will go quite slowly. Now for the second scenario, we would want to have a situation where all of the quantities are the same except for this aerodynamic coefficient c. So what can we think of? Well, let's say that we have the same person that is also traveling through air towards the ground and also with the same parachute, so the same cross-sectional area. But let's say now that this person, for some reason or the other, has its parachute upside down. Now intuitively, we know of course that even though all of the quantities are the same, this person will go towards the ground at a much larger speed. So let's now quantify this difference and look at the terminal velocity in both scenarios. Let's first look at all of the quantities that are indeed the same. We have of course the cross-sectional area, which in both cases is the same. So it will be this largest area of the parachute. And since it's the same parachute, it will be the same. And let's say that this will be a disk with a radius of 2 meters. So the area will be pi times 2 meters squared, the simple area of a disk. What is also the same is the mass of both situations. Let's say that in both situations, the parachute and the person together weigh 75 kilograms. The next quantity is of course the density of the medium, which is the density of air in this case, and is also the same between the two scenarios, 1.2 kilogram per cubic meter. And of course, what we also needed for terminal velocity was the gravitational constant, which is very evidently the same for both scenarios. And what is of course different between the two scenarios is this constant c, this aerodynamic constant, which says something about the shape of our object. And the shape is clearly a lot different between these two cases. In the first case, this aerodynamic constant is very large. It's 13.3 approximately. And because this is so large, it contributes a lot to the drag force, which counteracts the force of gravity. Now for the second scenario, for our second person, which is not so fortunate, the aerodynamic constant is much lower. It's around 0.5, or the aerodynamic constant for a simple sphere. So let's see now how the terminal velocity between these two cases differs. We know that the terminal velocity is equal to the square root of 2 times the mass times the gravitational constant divided by the density of the medium times the cross-sectional area times this constant c. And it will be this constant that will be of course different for both scenarios. So what we can already do is for both cases fill in all of the quantities that are the same. So the mass, the area, the density and the gravitational constant. So we get 2 multiplied by 75 kilograms multiplied by 9.81 meters per second squared divided by the density of air, so 1.2 kilogram per cubic meter, multiplied by pi times 4 meters squared, which is the area, multiplied by c. And it's of course this c that will be different. If we calculate this terminal velocity, then we see that in the first case, with our normal parachute, we get a terminal velocity of approximately 10 kilometers per hour, which is a very manageable speed to hit the ground. And it is for that reason that parachute people do not die when they hit the ground. For the second case, however, we have that the terminal velocity is approximately 50 kilometers per hour. And this is of course very problematic, because if you fall at 50 kilometers an hour on the ground, chances are very large that you die. And so it's very important to always check that you have your parachute the right way up. And we conclude from this exercise that the shape of our object makes a huge difference in how large the force of drag can be. In some cases you want it to be very large, for instance when deploying a parachute, but in most cases you want this to be very small, for example in race cars or in any electric car to save power. And this brings us to the end of this video, and I hope that you really learned something and are now more familiar with the force of drag. If you have any questions, leave a comment in the comment section below. And if you like this video, give it a thumbs up. If you want to get notified by future releases, consider subscribing. And with that, I'll see you guys in the next one. Bye.